Hi, everybody. My name is Daniel Gonzalez, and I'm a postdoctoral fellow at the Robotics Research Center at West Point. I'm here to present work conducted during my PhD with Professor Harry Asada at the Darbeloff Laboratory in the Department of Mechanical Engineering at MIT. This video presents our ICRA paper on passive quadrupedal gait synchronization for extra robotic legs using a dynamically coupled double rimless wheel model. Yes, that's me walking down the slope following our physically realized system, which converges passively to the desired gait cycle within several steps. The Extra Robotic Legs system was designed to assist workers for the U.S. Department of Energy who inspect and decommission nuclear sites. The average age of these workers is around 50, and when they conduct this kind of work, sometimes on hot and humid days, they must wear heavy hazmat suits and other protective equipment that weighs over 30 pounds or 14 kilos. The limited air they carry and the potential for heat fatigue or back injury limits the amount of time they can stay at a task location. Being able to carry a cooling system and extra air would make their job easier, but it would be too heavy without some kind of augmentation. This is why we designed the XRL system. It's essentially a backpack with a pair of articulated robotic legs that walks with the human operator while bearing the equipment payload. In order to achieve stable walking with the human operator, the locomotion strategy should be a stable limit cycle that returns to a desired footstep pattern when perturbed. It should maximize the margin of balance safety, and it should minimize the amount of energy lost due to footstep impacts. We can achieve these requirements by following a very special quadrupedal gait cycle. In this gait cycle, called the crawling or direct registering gait, the rear leg footfalls lead the front leg footfalls in such a way that the front and rear halves are synchronized, but 25% out of phase. You can see this bobcat following this very gait cycle. To maintain static balance while walking, the center of mass projection onto the ground should lie within the support polygon. Of the possible 4-beat footfall patterns achievable by quadrupeds, this gait cycle maximizes the center of mass margin from the edge of the support polygon. 4-beat walking with the front and rear synchronized out of phase and the footfalls maximally distributed in time exhibits minimum energy losses, leading to the fastest steady-state passive walking speeds. Intuitively, the more the footfalls are spread out in time, the more the system resembles a wheel. Perhaps most intriguing is that the front and rear halves of a quadruped following this gait cycle exhibit the same energetics as two bipeds walking 25% out of sync. If the Human-XRL system can be designed to passively synchronize to this special gait cycle, we can supplement this natural stability with feedback control. First, the system is modeled as dynamically coupled rimless wheels. The dynamics and convergence of this system are analyzed by non-dimensionalizing and simulating the system to generate a Poincare return map. The spring and damper for the coupler are chosen based on the fastest convergence. This convergence is then demonstrated on human-scale rimless wheels with the designed coupler. To understand our model, we must first understand the canonical rimless wheel. This passive model captures the natural dynamics of bipedal walking, using only gravity to inject energy into the system. It's essentially an inverted pendulum of length L on a surface with slope gamma during the stance phase. Gravity acts on the pendulum angle theta relative to the surface normal, governed by this equation of motion. We provide a constant step angle alpha, which marks the angle of forward lean when the wheel takes a step with the other foot. When it takes a step of constant length sigma, a hybrid dynamic switch is triggered. Instantaneously, the new foot becomes the pivot point and the initial conditions are reset. Only angular momentum about this new point is conserved, slowing down the wheel velocity proportional to cosine of 2 alpha. The center of mass does not move as the new angle is now negative alpha. During steady-state walking, the remaining momentum is sufficient to vault the pendulum over the vertical and gain momentum again. What we did was take 2 of these rimless wheels, which can operate independently, and connect them with a spring damper to get the dynamically coupled rimless wheels model. Each rimless wheel still triggers its hybrid dynamic reset independently, but the mass centers influence each other through a dynamic coupling. The 5 state variables correspond to the momentum and gravitational potential energy for each rimless wheel and the energy stored in the coupling spring. S is the step length between the stance feet of the front and rear rimless wheels. Because the wheels move a constant amount with each step, S is also discrete. S increases or decreases by sigma n times, where n is the difference in number of steps taken by wheel 1 and wheel 2. Including the dynamic coupler gives us 3 nonlinear state-determined dynamic equations of motion, which can be simulated using an ODE solver. From now on, we are assuming the front and rear wheels are identical. As the system begins to walk out of sync from initial conditions, the wheels speed up toward their steady-state velocities and eventually synchronize to 50% out of phase. Because we make no distinction between the left or right legs here, the desired phase difference in this model is 50%, rather than the 25% with a 4-legged model. We can see a trend here when the front wheel takes each step k. The rear wheel angle, theta 2, converges to 0. To quantify this convergence and be able to pick the spring and damper parameters that give the best performance for our system, we need to find the next theta 2 as a function of the previous theta 2. This function is called a Poincare return map. For a single rimless wheel, the Poincare map for the new angular velocity as a function of the previous angular velocity can be solved for analytically. Here, a surface of section in the state space is taken during the collision, and stable hybrid limit cycles in which the velocity is equal from one collision to the next are observed along the unit line. The coupled rimless wheels model has a larger state space, and its full Poincare map cannot be easily calculated. A linear Poincare map can be computed numerically and still capture local stability. We will call this matrix A. This discrete system is stable and thus converges to a hybrid limit cycle if and only if the eigenvalues of matrix A are less than 1. The system was simulated with many combinations of initial conditions and design parameters. Stiffness and damping combinations that exhibited convergence for all initial conditions were identified, and their trajectories were used to form a linear Poincare matrix using least squares regression. Here are the eigenvalues of each of these valid Poincare matrices. For our case, the best parameters were about 1/2 newtons per meter and about 88 newtons per meter per second. A non-dimensionalized form can be found in the paper to scale these parameters for any sized system. Using these values as guidelines, stiffness and damping parameters were chosen to match available off-the-shelf components. In less than 20 seconds, the front and rear rimless wheels have synchronized in this simulation. To test this, a physical coupled pair of rimless wheels was fabricated to achieve human-like step lengths of 15 degrees and a leg length of almost 1 meter. Each rimless wheel is constructed from aluminum rods, 3D printed brackets, and rubber caps for feet. The coupler is made of an extension spring and dashpot, with a linear bearing preventing unwanted forces on the coupling. April tags were placed on the side of each rimless wheel to aid with data collection. 2 experimental trials were conducted. The wheels were sent down a gentle 2-degree slope, with an initial out-of-phase condition. You can see toward the end of the run that the gait cycle has converged to be perfectly out of phase. By tracking phi, the difference between theta 1 and theta 2, convergence can be observed in under 10 steps. The same convergence can also be seen in the second experimental trial with different initial conditions. Taking a look at some snapshots from the first experimental trial clearly shows convergence to the desired 50% phase difference from the initial condition. This passive method of gait synchronization, combined with a well-designed controller, shows promise as a means of enabling the Human-XRL system to achieve stable locomotion. Thank you for watching our presentation. Please do not hesitate to contact me with any questions you might have. Stay safe, everybody.